Speaking of opinions, today's lab is going to be about power regulation for high current circuits. Not intensely high, but say I might have a 7805 and it's rated for maybe an amp or so, and maybe I need 5 or 8 amps. So can I just take these? Can I just take these and parallel them? Can I just put them together like that? Because we know that, paralleling batteries and so many other things, that the current will it'll allow more current through. So is this the case? Can we do this? Should we do this? Will the internet revolt if we try? Well, as you can see from the article that we're staring at right here, paralleling linear regulators must be easy, right? Well, turns out it's not exactly the case. So what the issue is inside of your typical linear regulator, you're going to have, the way it's generating its output is based upon its voltage reference and the feedback resistor internally. And like all other components, these have some level of tolerance in there. So if you were to buy a handful of these, maybe right off the press, and maybe they're all very much the same, maybe they'll work fine. There's a handful of people talking about this online, how hey, don't ever do this, and then somebody else pops in and says, hey, I did this when I was a kid and I've had it for 20 years and it's working fine still. So it could be okay. But I think that most people understand that over time there could be a problem, and if you were to introduce other regulators into the mix that didn't have the same amount of deviation from tolerance in there, right? That you're going to end up with more problems. And so then what happens is, because of the amount of tolerance or the offset, the deviation between them, one of these will have a higher voltage than, say, the other, and then that's going to be, let's say, the preferred one. And, well, not preferred, but you're going to get most of the current from one rather than the other. It's not going to be doing the load balancing like you would like it to. And then events could arise, right? It's all in all one of those kind of things that might work okay for a hobby, and you might get it to work with a few different little modifications, like adding your own external ballast resistors and possibly even some other kind of feedback loop inside there. You might get it to work, but for a production system, it does not seem to be the case that it's going to be good, that anybody would say that it would be something that you would do. So to this thing that I'm looking at right here, I was looking around for what to do with this, and I ran across this article from Kevin Scott at Analog Devices, which is linear tech, of course, right? And so I'm scrolling through this, and it says, this is why you shouldn't do it. Basically, repeating everything I just said here and giving you a few examples on how you might get around it. So what they are saying is, yes, you can do it, but here's kind of a circuit that you might want to do to, get it to work, or say like down here. So you're adding the external resistors, and then you could do it like this, and then you get more crap going on and more parts to buy, and more and more and more. And so then by the time you get down to the end of the article here, they say, or you could just go get yourself one of these LT3080s. And these are designed to be put together. And as a matter of fact, they even mentioned that the LT3080-1 has a built-in ballast resistor, so you don't have to hardly do anything. And you can see from this diagram right here, it's not as simple as just paralleling a bunch of, regular plain old 7805s, but it seems pretty simple, right? And you could dial in the output voltage to whatever you like with your external resistor. Now here enters the next problem, though. So I was pretty hot on this. I thought this was going to make a good lab. I thought this was going to be good for the way we're going to do this. We'll go for it. Well, as it turns out, these right here Here's one of them. They have them in a couple different packages, but 36 volts, or wait, there we go. 36 volts max output, that's good, with 1 amp. So, okay, well, let's say I need 8 amps or so. I'm going to need a handful of these. So I'm going to need, well, probably at least around 8 or so just to be on the safe side. And but that's fine. And it takes an input of max of 36 and output. That's going to meet my needs. I want 5 volts at, let's say, 8 amps. And so everything is all great looking, right? And then you come up here and you find out that one of these things is $5.74. I looked over at Mouser, they got it too, and it's about the same price. Okay, so I'm like, well, I don't know. Maybe I'll do it anyways because I'm all down for like doing something, wasting some money, not wasting, but spending some money to test something out to see how it works because you never know when the knowledge gained might be usable and by you in a different situation in a place that money doesn't matter. So great. And then I just keep thinking about it. I'm like, no, it's not going to work. There's got to be a different way. So essentially what I did is I spun my head around and I came right back to almost where I started a while ago in a project very similar to this, is let's just drop the whole linear regulator thing and let's go with this. So here is a switching regulator. It actually has an LDO second out that you could use, but we're going to use it as a switcher. And it is $2.54, which again, that's maybe kind of expensive, but you only need one. This one here, output 1 will do 5 volts at 8 amps, job done. There's my device. Now, if I go to the data sheet on this, the typical application circuit does require some extra equipment, some extra components here, but not too bad. Definitely more than the 3080, but it's okay. So this is what we're working on right here. This is going to be our circuit. So let me zoom into this here so you can kind of take a look at that. Now, this video here is an overview on the concept, the needs, some of the issues, and then we'll see where we get from there because I have not built this yet. I perceive a couple problems with this. I have a couple questions about this. So we'll see how it goes. Again, this is just concept and development. Now, the skills that I want to have people gain from this, rather than have a project where, here, build this thing that you were told, build this kit or something like that. This one here, I think, is probably a really good idea for anything to build something from the typical application circuit on a data sheet, because this I feel is again getting as close to real life situation as possible. I have a need. I need to find a chip that will do this for me. I need to find a component that will do this for me. I found one right here. I look around. Are the components accessible? Yes, they are. Is it going to be cost prohibitive? Doesn't seem to be the case here. These are all pretty much, not terribly too much. This cap over here, maybe, a few more dollars than, 10 cents for some of these. The inductor is a little bit, but it's all pretty okay. So then you pull the trigger and you say, let's go ahead and get this and build it up. So that's what we're doing. Now, I do have some questions still about how this is going to operate because, we haven't done it yet before. But if you want to play along with me, go ahead and purchase all these things. I'll have a link to the data sheet here in the comments or in the in the description down there. This video won't see public light of day if this doesn't work. Okay, so if you're seeing this, there should be right in the section there in the playlist, there should be a part 1, part 2, part 3, or whatever it does, however many to get this thing done. My intention is to get this all designed up, make a circuit board, do that whole thing, KiCad, send it off, and put it together. Now, my questions, let's see, I'll just kind of go through some of these here. All the components you can find, I found them on DigiKey. That seems to be the one I go to the most. Nothing against Mouser, fine. I just end up at DigiKey more frequently. I was able to get everything there. Everything here should be pretty cheap. Your inductors, maybe a little bit more for that, but I mean your resistors, your caps, those are usually on order of like 10 cents to maybe 40 cents, okay? Now, I was able to find everything by their value pretty darn close, except for this one right here. I couldn't find the 88 microfarad cap right here. And so I just want you to kind of think about the circuit in its whole, about maybe what's happening here. And I'm going to show you the section in here that explains what each one of these pins do, so to help better inform you. Now, the cap here, I ended up spending a little bit more money on. I forget what it was, but I started looking at this, and I'm pretty certain, that this thing's, job in life is as a smoothing cap over here for your V out. And so then looking at it that way, do we need an 88 microfarad? Does it need to be that? Could it be more? Could it be less? Well, if it's for smoothing, then probably, a little bit more is going to be maybe better than a little bit less, potentially. And if we did have a little bit of ripple on it, what's it going to do to my circuit? Is that going to be a problem? So what happened was I started looking for, ceramic caps. I went to Tantalum's. I went to, all the various different ones that they had there, trying to find one. And they did exist, but they were like, some of them were like $45. So you kind of know you're in the really wrong area if a small component like this costs that much. So what I ended up doing was looking for something like, in DigiKey, you can do a multi-select for the items here, and I looked for anything between, say, 88 and 100 or so, right? And I ended up going with 100 microfarad electrolytic capacitor. I think that that's going to be the best. It's rated for more voltage. It seems like it's going to do the job just fine right there. So I did make a kind of a choice right there. Let's see, what else was of an issue? This one right here, 3.3 ohm. Between this and the bootstrap pin, I could be wrong about this, but I felt that it's so small and it's such a specific number that it might be kind of important. So I looked for one that had only 1% tolerance on it. So maybe that'll help. I'm also thinking that some of these in here, they might benefit by putting in a very small trim pot, potentially, or maybe just let it be a trim pot, as long as you could lock it down, I guess. Okay, so I think those were the main things there, main little things. Then the one that was a huge, not explained gray area is right here, your enable pin. So your enable pin turns the thing on, and you wouldn't get that from the application circuit. It doesn't show it there. It seems like it's just hanging out here, not being connected. What you need to do is provide it a certain voltage, very, very small current. I think the current was like 5 microamps. I mean, it's really, really a small amount. But you need to get it from somewhere, and you're not going to put a battery in here just for it. It's something on the order of like 2 volts, I believe. I'll show you in a second. 2 volts at some really small amount of current. So what you need probably to do, my again decision, what I did here was to pull off the main a really high like meg ohm voltage divider in here, just to get that to come on. And so it explains that if you want it to come on immediately, that's probably the proper way to do that. Okay, so copy this. And you might as well even throw this into KiCad, because that's where we're going to go to next with this in separate video. We're going to get this whole circuit built up. We're going to make the footprint for our chip. And anything else we need to do, start wiring things together. Then get this data sheet and go through it. Not every graph, not every, Tempco, everything in here. Just look at these will be kind of important in a second. I'll come back to this specifically right in here. Well, here's your EN value that I was talking about. So it's 2 volts at 5 microamps. Okay, so that's what that thing needs typically. And what it is this right here. So this is where you're going to go. This is what you're going to read on to see what how this thing functions and see if you can read this, go back to the typical application circuit, and see if we can begin to understand how it's going to work. Things I like about this that tells me that this is going to make a really good, realistic lab is that besides just, letting us know what these pins do, it gives you other specific real life manufacturing pieces of information, specifically things like the traces, the size of the traces. Here it tells you that you better make sure on VN you're going to need a decoupling cap. Make sure you use wide PCB traces. Down here on V out, which is used to sense the output voltage of the buck regulator, make sure that your traces are at least greater than 25 mil, and make sure that you keep the V out sensing trace far away from the switch node. So avoid vias on the V out sensing trace. So they're giving you more information to help you manufacture your board. You would not get that in any kind of a breadboard lab. So I'll go ahead and go through this and kind of hit some of the high points, but really I want you for homework to go through each one of these and try to understand what it's saying and correlate this with the application circuit above. As you go through the list, you will find a handful of things that are pretty typical, things that are going to be familiar. Make sure that you do read very carefully, though, because, again, there's a lot of good specific information in here, and you'll find that some of the things that say what they are is maybe not so much what they are. Not that I know everything about this, but I've read the data sheet already. So now, if I scroll down here a little bit further, what I want to point out is this right here. I want to talk about the enable pin itself. So this is going to enable the buck step down regulator in here, and that's what we want. And so we want this thing to be on, and this is what turns it off and on. They talk about it here, but it says if you connect this through a pull-up resistor or a resistive voltage divider for automatic, you'll get the automatic startup. Do not float this pin. So we want to get this thing, turned on. We're going to have to do a voltage divider, because otherwise, kind of things like, some H bridges and things that bite you in the ass because you don't hook up your damn enable pin, right? So we'll need to get this operating, and that's what I was talking about, the extra resistors. So we could I'm thinking we'll create a voltage divider off of the main power, right? So we're going to have, in this case, incidentally, we're going to have, it's a 4S LiPo coming in, so we're going to have 14.7-ish volts as our in, and we need to knock that down to the power specified for the enable pin, which we saw earlier is 2 volts. So then I will leave you with that. This is the NB679, and this is the focus of our next lab. So this is going to be kind of a hard one. Do not feel like you need to study the entire data sheet, but make sure you get all the obvious high points, okay? And study this thing right here, read the pinouts, try to get a handle on what they're doing, buy the components if you are watching this online, and go ahead and follow along. Again, if you're seeing this video, then it's complete and it functions, so feel free to go online and find all the things you need and start getting your KiCad documents all in order.